Hello everyone, welcome back. Now today we're going to explore or revisit geometric progression. Okay, let's take a look at this question here that is related to the geometric progression. All right. Now we are given a sequence here that consists of all these numbers here. Now we need to show that the sum of the first two n terms of this sequence is given by, I think this is a half, all right? So this is a half, 3 to the power n minus 3 to the power 1 minus n plus 2. All right, now we need to prove this, whether that is true or not. So I think there's a half here. Yep. All right, let's get started. Okay, now the sum of the two terms. I'm going to show you a very simple analogy first before we get into the analysis. So now let's take a look at this analogy. This is something like, I wouldn't say analogy, it's more like a simulation. Yeah, okay. Let's call that simulation then. Small simulations just to help us to understand further what we are referring to as 2n here, right? So take for instance, you have 1 plus, because we are interested to um, provide the sum of the 2n terms for this sequence here, right? Okay, now let's assume that in this simulations we have 1 plus 1 plus 3 plus 1 over 3 plus 9 and plus 1 over 9 here. We have 1, 2, 3, 4, 5, 6, 6 terms. So here we have 6 terms here. Oh, we have 6 terms. Okay. So what happens is that if you are interested to sum this up, we'll say that we are actually summing 6 terms up, right? Or we can actually rewrite as sum of 2 multiplied by 3, because 2 multiplied by 3 would also yield sum of this 6th term. Now the reason why we write as a sum of um, two parts, I would say two parts of that consists of 3 terms each. Okay, now let me show you what do I mean by that. All I need to do is separate out the terms that are relevant or that can be grouped into their own class, right? So in this case, we have 1, 3, 9. So I'm going to group those integer numbers together. So you can see that 1 plus 3 plus 9. Okay, how many terms are here? We have 3 terms here. And then not only that, because we need to sum up this series, therefore we still have like a 1 here, and then we have 1 over 3, and then we have 1 over 9 here. And then we know that there's another 3 terms here. So in total, we are actually summing up 6 terms here. There are 6 terms, right? So instead of saying I'm going to evaluate the sum of 6 terms, I can say that I'm trying to evaluate the sum of two 3 terms, 2 series that consist of 3 terms each. Yeah. So that's what they actually mean. So you can say that if this is the case of 2n, for instance, then I should have 1 plus 3 plus 9 plus until until my n term here. So you can see that this is a geometric series. I would say geometric series, and then the n term for this would be 3 to the power of n minus 1 here. Okay, now there's the first part. It consists of n term. And then I need to have another sections that is consisting of another geometric series that consists of all these terms here. Until, I would say, if you want to write in the proper term, is like this. All right. Now there you have it. we also have n terms here. Therefore, when they say we want to find the sum of the first two n terms, what they mean is we are trying to sum up two separate geometric series that consist of n terms each. Okay. Now all we need to do is just sum up this first term that consists of geometric series that has a common ratio. So maybe I will label this part as my sum number one here, and then this part I'm going to label it as my sum number two. Okay, now I'm going to work out each one of these separately so that you can see how I'm going to obtain the final result. So this one here actually consists of geometric, it is a geometric progression or geometric series here. The common ratio, I will use R to represent common ratio, is actually a 3. The first term is a 1. Alright, now by using the formula for the sum of geometric series, which is a Rn minus 1 here. Now I'm using this formula due to the fact that the restriction is set on the common ratio is greater than 1. I know that the common ratio is greater than 1, therefore I'm going to use this. Okay, by substitute all the results that I have discovered here, I would end up with 3 to the power n minus 1, and then that will be a 2 here. Okay, now that's my first part. Then I'm going to proceed on with my um, summation number 2, which also consists of geometric. Okay, maybe I'm going to write down my geometric series over here. So this is my second geometric series, and then this geometric series consists of a common ratio of 1/3. The first term is still the same, it's still a. So therefore, by using the same formula, sorry, it's a different formula. It's supposed to be 1 minus Rn, 1 minus R, given that the magnitude of R must be less than 1. So that's the reason why I'm using this. So from here, by substitute all this, I will get this as n, and then 1 minus 1 over 3. Okay, now of course you can simplify this. All right, if you simplify this, we would end up with, okay, now in this case you will have, I would say 3 minus, okay, these two can be combined. That will be 1n here over a 2. All right, now I hope you are clear how I reach this section here. All you need to do is just multiply your numerator and your denominator by 3. Then you can simplify in such a case. And then after that, you need to apply the exponential rules here. Okay, right. Okay, I hope that is clear. All right, maybe I'm going to show the step by step in case in case you don't see how I reach this conclusion here. So first of all, I'm going to multiply my denominator by 3, my numerator by 3 also. So therefore, I'll get, so that is 3 minus 1 here. Okay, and then this term here, I can rewrite as 3 to the power negative n. So that will be 3 multiplied by 3 to the power negative n, a 2. Okay, so from here, you can see that by using index rule, this is a 1 here. Therefore, I can write this as 3, 1 minus n divided by 2 there. And then there you go. And then finally, all I need to do is obtain my sum of my two n terms, in this case, by summing up these two results. So my first result is n minus 1, and then my second result is 3 minus 3, 1 minus n divided by 2. And then you can see that by factorizing, okay, and then I have this So therefore, in this case, I will have, I'm going to collect all these terms together, for instance, and then the number, I can leave it at the end. Therefore, it is proven that yes, the sum of this series for the first two n terms is actually given by this. Now, of course, you can try out, for instance, for checking purpose, you can say that let's assume that I'm interested to find these uh, first six terms, which is actually the first uh, three terms actually. So all I need to do is just substitute my n equal to 3, for instance, okay, to see whether I'm actually getting the sum that I wanted or not, right? So the checking, I leave it to you. I hope that is clear how we um, apply. I would say this strategy is more like divide and conquer, right? Which is a very useful strategy that is used in um, gaming especially. Usually for me, I prefer to apply it in mathematics also, right? If you find it useful, do try it out, right? Now I'm going to show you the uh, second examples of geometric series. All right, stay tuned. All right, let's take a look at the second questions of the geometric series here. Right? So here we are given the sum of the n terms that involve these numbers given as 6 plus 66 plus 666 and so on and so forth. We need to find the sum of the first n terms of this sequence. Right. Now, we may not be able to recognize or maybe we are not able to make use of any standard sequence that we have learned before, unless you try to come up with your own sequence or technique, right? But for me, I would try my best to figure out how can I make use of those standards arithmetics progressions or geometric progressions that I can make use in this case to further ease my analysis. Right? Let's take a look at how we can do that. Right? Now, maybe applying divide and conquer strategy again might be useful. But yeah, who knows? Let's give it a try then. So first step, I'm going to rewrite this one more time. So that will be 6 plus 66 plus, and maybe I'm going to write as maybe I'm going to write 1 2, okay, 4 terms is sufficient here until of course we have the rest of the terms, right? So take for instance, and so on and so forth, right? And then we also notice that this summation here can be written as 6 here. We can also write this as 6 plus 60 for the second term. Now we can see that, oh yeah, there is a pattern that we can work with by applying divide and conquer strategy here. And then we have here. Now that will be this term. And then after that, I'm going to do that for the next one there. I might be a bit lengthy, but it's okay. Okay, now that will be this term. Okay, and of course, we have until n term. I would say n term here. You can see that the first term has one term. The second one have two terms. The third bracket has three terms. Therefore, when we reach to the n term here, the numbers in the bracket should have n terms. So it should be the sum of the n term here. I'm going to rewrite that. For instance, 600 until, yeah. So that would be until, now let me see. until wait, okay, until, okay, let me see. I think it's better if I write it down at this at the end here. Hold on. So we're going to add this until we have 600, 6,000, and so on and so forth until the last term here. You will recognize that all the terms in the bracket here is actually geometric progression or geometric series here with a common ratio of a 10. Okay, so therefore I can actually write this down as common ratio is a 10, right? Yep, correct. So common ratio is a 10. That will be 10 n minus 1 here until 10 n minus 1. Okay, let me see whether I got that correct or not. That is the first term is a 6. Sorry, I forgot that. So there's a 6 here. All right, so there you have it. This is the sum until n term when we reach the last term here. So we have n terms inside the bracket. All right. Okay, so I hope that's clear. And then next, we're going to rewrite this in a more explicit form so that we can recognize further patterns that we can work with. Now, in this case, we know that 6, all the terms in the brackets are geometric series or geometric progression in this case. So therefore, I can apply the formula for the sum of geometric series, which is given by, here I'm going to write it down, which is given by, I know that the common ratio is a 10, so therefore I should be using this formula instead, r minus 1 here, knowing that the magnitude of r must be greater than 1. Okay, now I know that in this case my common ratio is a 10, so it is indeed greater than 1. So therefore, I'm going to apply this formula so that it can represent all the sum in the bracket there. So the first one, because it's the first term, so that is typically 6. Common ratio is still the same, it's a 10. So 10 to the power of, because the first term is a 1 minus 1 divided by 10 minus 1. Right now, that's my first term. Then the sum of all the terms in the second bracket will be given by 10 to the power of 2 minus 1, also 10 minus 1 here. And then my third term, that will be 10 to the power of 3, also 10 minus 1. And then my fourth terms, that will be 6, 10 to the power of 4, divided by 10 minus 1. And of course, until my last n terms. So for my last n term, it will be 10 to the power n, of course, minus 1 divided by 10 minus 1 also. And then you will notice that all of them share the common factor of 6 over 9. So I can take out the 6 over 9. All of them share 6 over 9, so I'm going to take that out. Okay, so that's what we have. Of course, you can further simplify that. Alright. And then you notice that we do have -1 repeat themselves. How many times? N number of times because there are n terms here. Right? So therefore, I'm going to divide and conquer again. Here I have 10, 10 to the power 1, 10 to the power 2, and so on and so forth until I get my 10 to the power n here. And then after that, I have 1, 1, 2, 3, 4 here until my last one here. I'm going to put a bracket there. Okay, now that's how it look like. And then you will quickly recognize that this is a geometric series, of course, with a common ratio of 10, which is exactly the same like before. Therefore, we can rewrite the sum of this series as 10, 10 to the power of n minus 1 over 9 here. And then now we are trying to sum up all the 1 repeatedly for n number of times. So therefore, we have to minus n. This is like 1 plus 1 plus 1 n number of time. So basically it's just n. All right, now I hope that is clear. Now, of course, if you want to restructure this, okay, based on my preference, okay, you may have your own preference. Go ahead with that. Okay, based on my preference, it will look something like this. I prefer to take out my 9 here. Therefore, I will have 10n minus 1. Okay, minus 9n here. Okay, now therefore, that will be the sum of the first n term there. Now, if you like to check, for instance, for checking purpose, I always like to check in this case to see whether my n term is correctly evaluated. So take for instance, if I'm interested to evaluate the first 3 terms here, which is if we add this up is 730, it should be 738. Okay, so if I wish to sum up my first 3 terms, which is this, that should yield 738. If you add them up manually, it should yield 738. Now then again, if I use my formula here that I have deduced, I want to check whether it works or not. Now letting n equal to 3 here, so that will be 10 to the power 3 minus 1 minus 9 by 3 here. Okay, so that will be 227. And then this part here will be 9,990. Okay, this one should be 999. Okay, minus of 27. All right. So if you use your calculator to evaluate this, okay, I just want to check very quickly, see whether I got this correct. Okay, hold on. I will have 0 minus of 27. Okay, divide by, oops, hold on. Okay, so after that I need to divide by 27, for instance, and then multiply by 2. Right, so the answer is indeed 738. Okay, now that's just a quick check. I wouldn't know that whether it's um, absolutely correct, but if you are interested to verify whether this is correct, you can apply a more systematic methods like mathematical inductions to prove that this is exactly the correct formulas to evaluate the sum of the n terms. That one I'll leave it for you guys to figure out how to apply that. But for this context, we are only interested to get the sum of the first n term using a divide and conquer strategy. Right? Now, I hope that has been a useful learning strategy for you. Right? Until I see you guys again, take care, everyone.